part 4 of LPSC solutions. So I was planning to do this video as a last part, but I think that we have to do one more part. In this video, we'll be seeing some questions, some twisted type of questions and some theory type of questions which are most commonly seen in competitive examinations. Okay. So in this video, we'll be seeing some twisted type and repeatedly asking questions. Okay. So let us see what is the first question. In a 50% modulated signal, that is the modulation index is given as 50% or 0.5 is the modulation index. The carrier is suppressed for transmission. The saving in power would be. So this is a typical type of question which is commonly seen. And if you study this type of one question, you will be able to answer all these patterns. Okay. So how to do this problem? So as I said in the previous parts, that is part 1 and part 2, in this question paper, there's a lot of question that is coming from this modulation area connected to the modulation index, power and everything. So this equation, power equation is given a lot of importance in this question paper. So the equation is, we need to find the transmitted power PT is equal to PC, this is the relation, 1 plus m square by 2. This is the relation of transmitted power with carrier power and modulation index. This is a very common thing. Everybody will be knowing this. So, and also if you have seen part 1 or part 2, you'll be knowing this. So what is m here? It is being given that the signal is 50% modulated, means 50 by 100 or 0.5 is the modulation index, right? So this is how you need to find the modulation index. If you are being given that it is 50% modulation or the modulation depth is mean given, is if such a thing is given, you should use this relation that whatever percentage is being given, that by 100 will be your modulation index. Very simple. So 0.5 is the modulation index. So you can substitute it here, 0.5 square by 2. So you will get the relation PT is equal to PC into 1 plus 0.5 square by 2 is equal to nothing but 1.125 is the relation. Okay. So PT is equal to PC into 1.125. Now, in the question, it is been given that the carrier is suppressed. Okay, so what will happen if the carrier is suppressed? That means the carrier won't be present inside the transmitted signal. There will be only the two side bands, lower side band and upper side band, right? So, how to do this? That is, how to do such a problem is, take the ratio of PC by PT. Now, you have PT is equal to PC into 1.125. So from this, you have to take the relation PT by PC. What will be that? PT by PC, I'll write it here. From that, PC by PT is equal to 1 by 1.125, or you will get it as 0.888 up to, that is recurring. Okay, so if that is PC by PT, you have obtained as 0.888, right? Or you can write in terms of percentage, it is 88%. The ratio of PC by PT is equal to 88%. That is, out of the total transmitted power PT, PC, how much amount is present as PC? That is, how much power is contributed by PC, that we are finding here, right? So, if you are taking the ratio PC by PT, you are finding out of the total power PT, how much is contributed by the carrier, or PC is how much? It is 88%. Now in the question it is been asked, how much power is saved if the carrier is suppressed, means this much power will be saved, right? Because out of the total power, this much is contributed by PC, and if it is removed, this much of power is saved. Very simple. So from the options, the correct option coming is option A, which is 88.9. Okay, I hope that this type of question is now familiar to you. You only need to know this relation that PT is equal to PC into 1 plus n squared by 2 to answer this question. Then you have to take the ratio of PC by PT. You will get a percentage value, that much of power percentage is contributed by the carrier side. And if it is suppressed, that much of power is saved. I hope the concept is clear. Correct answer is option A is the correct answer. The question that we are going to discuss is this. It is also a little bit tricky question, but if you know the concept and if you have answered at least one type of this question, you will be able to answer. Okay, I'll read out the question. I have not included the option because from the option you can easily find out because there are three things we need to find. From the first thing itself, you should be able to find from the option. That is why I have not included the option. Okay, I'll remove this in order to make some space. So the question is, the peak output of a tuned amplifier is 6 megahertz. So this is again considered to resonance tuning and everything. So the question is, the peak output of a tuned amplifier is 6 megahertz. So the quality factor is 60. Quality factor is 60. The bandwidth and 3 dB frequencies are dash. Okay, so in order to answer this question, I'm going to draw the resonance peak first. Okay. So this is the resonance peak. This is the peak value of current, and this is the frequency contributing to the peak value of the current. I'm just drawing a rough figure. Okay, there are two frequencies which contributes to the upper edge band, side band and the lower side band of this peak, and that contributes what? Bandwidth. In between these two peaks, or in between these two frequencies, consider this as F1, this is F2. Okay, I'll draw it a little more neatly. 1 minute. Consider this is your peak, right? This is the frequency which is the resonance frequency FR. There are two other frequencies which contributes the 3 dB frequencies or edges of this peak, which consider it as F1 and F2. And in between this frequencies F1 and F2, whatever be the width, that is called the bandwidth of the peak or the resonance curve. Okay, so what is been asked in the question, I'll read it once again. The peak output of the tuned amplifier is 6 megahertz. Means this FR or this peak frequency or this maximum resonance frequency, that is whatever at whatever frequency the peak is going to the highest value, is given as 6 megahertz. From that, FR is given as 6 megahertz and also the quality factor Q is given as 60. Now, the relation between quality factor, resonance frequency, FR is a resonance frequency, and the bandwidth is already discussed in the part 2 or part 1. That is, Q is equal to FR by bandwidth. So, from this you can directly find the bandwidth which contributes to the first part of the question. And bandwidth is equal to FR by quality factor. That is 6 megahertz by 60. 6 megahertz by 60, it is nothing but 100 kilohertz will be the bandwidth, right? 100 kilohertz will contribute to the bandwidth. Now, so it will be a meg by 10 raised to 5 hertz. It will come those. So you can write 10 raised to 5 hertz is 100 kilohertz. Very simple. Bandwidth is 100 kilohertz. So now one thing you understood. See, this is the 2 3 dB frequencies F1 and F2. F1 and F2 contributes to the 3 dB frequencies, and in between these two 3 dB frequencies or in between F2 and F1 there is 100 kilohertz. That is this much of F1, this is F2, this total frequency is 100 kilohertz, right? And the midway or the resonant frequency is 6 megahertz, right? Okay. So this much is 6 megahertz. This peak is 6 megahertz and total width of F1 and F2 is 100 kilohertz. So what will be F1 and what will be F2? So midway of this F1 and F2 is 6 megahertz. So this total width, so total width is 100 kilohertz. 100 kilohertz is equally divided towards this portion and this portion. Just use your logical thinking. You can find it very easily. So consider that this is 6 megahertz and there is towards this much is 50 kilohertz and towards this much is 50 kilohertz. So what will be F1 and F2? Very simple. 50 kilohertz can be written as 0.05 megahertz, right? This is very some sort of a logical thinking type of question. So only then you can find the 2 3 dB frequencies. So towards this lower side of 6 megahertz there is 0.05 megahertz and towards the upper end of this 6 megahertz there is 0.05 megahertz. Because this width is this width, you don't get confused with this. This width is 100 kilohertz. Okay. So you can write this as F1. I'll remove this curve. So you can write F1 is equal to 6 minus 0.05 megahertz and F2 is equal to 6 plus 0.05 megahertz, right? So F1 is 6 minus 0.05 megahertz and F2 is 6 plus 0.05 megahertz. So what is F1? F1 is nothing but 5.95 megahertz and F2 is 6.05 megahertz. Very simple, right? So this is how you need to solve this problem. Okay, so the 3 dB frequencies are 5.95 megahertz and 6.05 megahertz, and the resonance frequency or the midway between these two, or where the peak occurs, is at 6 megahertz, and the width of this range or the bandwidth is 100 kilohertz. Very simple. So this is how you need to solve such type of problem, and this is a typical type of question you can face in competitive examination. So please do at least this type of problem. You'll be able to answer any this series of problem. Okay. So how the question is going, I'll explain it once again. You are being given the resonance peak frequency, or the frequency at which the resonance peak is occurring. It is 6 megahertz, and also you are being given the quality factor. So from this you need to find the bandwidth. There is a direct relation, that is quality factor is equal to peak or resonance frequency by bandwidth. From that you can find the bandwidth. Then you need to find the 3 dB frequencies. See, if there is a bandwidth, there is a lower end frequency, there is a upper end frequency. You need to find these two frequencies. And also the midway or the peak frequency is also given. So you can split the bandwidth as 50 kilohertz and 50 kilohertz, or 0.05 megahertz and 0.05 megahertz. Then subtract this 0.05 from the midway. You will get the lower end and the upper end. Very simple, right? Okay, so the answers are 100 kilohertz bandwidth and 5.95 megahertz and 6.05 megahertz is the answer. Okay, I'll remove this to make some space. Next question is actually a theory question. There is a lot of confusing type of theory questions in this question paper. So you should also be very much aware of the theory concepts. Okay, I'll read out the question. What happens in an op-amp based integrator? Again, the op-amp is coming into the picture. If the input frequency is kept lower than the frequency at which gain is 0, that is 0 gain frequency, if the frequency is kept lower than the 0 gain frequency, what will happen? So op-amp based integrator is nothing but look like this. Inverting terminal, this is grounded. There is a input being given here. This is the input resistance. There is a capacitor in the feedback loop. This capacitor charges towards the period of integration, and thus the integration is happening. And if what will happen if the frequency of the circuit is being lower than the 0 gain frequency, what will happen means, if the frequency is kept lower than the 0 gain frequency, then integration won't happen. And since you are connecting this to the inverting terminal, this circuit will act as a inverting amplifier. The correct answer is that the options will be, it will work as a perfect integrator, it will act as a voltage follower, it will act as a comparator. So these type of options can come. The answer is, it will simply act as a inverting amplifier. Okay, that is a correct answer. Questions is this. Power input of an amplifier is 2 microwatt. The power gain is 40 dB. Output power is dash. Okay, so P out by P in is the power gain, right? That is a gain. But here the gain is given in dB. So gain in dB means that is 40 dB is equal to, it is actually 10 log 10 of the gain in ratio. So you can write this as, so in order to find the gain in ratio, just take 10 raised to 4, right? That is 10 raised to 4 is the gain in ratio. That is, take the anti-logarithm of that. In order to convert dB to the ratio value, take the anti-logarithm. That is 10 log 10 is actually gain in dB. So we have done this in a lot of examples. So you'll be knowing this. So gain in ratio is obtained as 10 raised to 4. Now this 10 raised to 4 is nothing but P out by P in. So what is P in? P out by P in is equal to 10 raised to 4. What is P out? P in into 10 raised to 4. So P in is nothing but 2 microwatts. That is 10 raised to 4 into 2 into 10 raised to minus 6. So 10 raised to 4 and to be 10 raised to minus 2. 2 into 10 raised to minus 2 watts. How can you write it? 20 into 10 raised to minus 3, right? You can write P out as 20 into 10 raised to minus 3 watts. It is equal to 20 milliwatts is the output power. Okay, so the correct answer is option D, which is 20 milliwatts. Moving on to the next question. It is a theory question. It is a very commonly asked question. The gain of a bipolar transistor drops at higher frequency due to dash. We know that in a bipolar transistor there is a lot of capacitors, coupling capacitor, bipolar capacitor, inter-electrode capacitors. What happens at higher frequencies is that when due to the higher frequency, that is when the capacitor is operated at higher frequencies, there will be some variations or some parasitic effect of this capacitor, and due to this parasitic effect, the gain of the capacitor is actually dropped. So in general, you can say that the gain at higher frequencies drops due to the parasitic capacitance effect in BJT. Okay, so it is actually due to coupling capacitor, bipolar capacitor and the inter-electrode transistor capacitor. So the correct answer is option D, which is both A and C. It is not due to early effect. It is due to the capacitance. Okay, correct answer is both A and C is the correct answer. For lower Q point of operation, dynamic resistance of diode is dash. For lower Q point values, as the Q point is reduced, the dynamic resistance is increased. Now, what is dynamic resistance? Dynamic resistance is nothing but change in voltage by change in current. It is called dynamic resistance. And for Q point operation, if you lower the Q point value, means the AC resistance or dynamic resistance is increased. Okay, answer is increased. It can be options like lowers, increases, higher or no change. It is higher value. Next question. A combination of two diodes connected in parallel when compared to a single diode can withstand dash. The answer is it can withstand twice the amount of forward current. So why we are actually connecting the diodes in parallel is because, see, when diodes are connected in parallel, it can carry or it can withstand more amount of current than a single diode. So if the total current to be handled by the circuit or the diodes is greater than the current rating of a single diode, we connect the diodes in parallel. So when connected in parallel, this circuit or this series connection, this parallel connection, this connection of diodes can withstand more forward current. So if the total current to be handled is higher, means we connect the diodes in parallel. Okay, so the answer is it can withstand twice the maximum amount of forward current. Okay, that is the correct answer. The next set of questions is this. The phenomenon of microwave signals following the curvature of Earth is called dash. It is called ducting. When the microwaves travel through the lower layers of atmosphere or the atmosphere, due to the atmospheric refraction, it follows a curvature or it bends. This phenomenon is called nothing but ducting. So please have an idea of it. So the microwave signals bend due to ducting. You need to find the output voltage. This is a simple question, but the difference from the other questions or the questions which we have discussed is that both the terminals, that is negative and the positive terminals, connected together, and the voltage is applied as a single supply or single volt. 1 volt is being applied to 1K and 1K. So what will happen here is that I have already written here. See, 1 volt is being applied to 1 kilo and 1 kilo means it will get equally divided as 0.5 and 0.5 volt. So the voltage coming to the negative terminal is V in minus is equal to 0.5 volt is coming. So what will be the current flowing through this 1 kilo ohm? It is nothing but, that is I 1K is equal to 1 minus, here there is a 1 volt, there is a 0.5 here. So 1 minus 0.5 by 1K, right? It is nothing but 0.5 milliampere will be the current flowing through this 1K. Now we know that there is no current. It is given in the question that this ideal operational amplifier, there is no current being drawn towards the input terminals. So the current flowing through 1K is equal to the current in the feedback loop. This thing we have discussed in the op-amp video. Please do have a look. So the current flowing through 1K is nothing but the current flowing through the 2 kilo ohms in the feedback. So what is I 2K, that is in the feedback, it is equal to 0.5 milliampere itself. Now, the equation for finding V out is nothing but, I'll write it here, V out is equal to V in minus this feedback resistance RF, we'll put the value later, into the feedback current IF. This is the equation. This we have discussed in the op-amp numericals part 1 video. Please do watch that video. Okay. 0.5 minus RF is 2K into 0.5 milliamps, right? So K and milliamps will get cancelled and the value is minus 0.5 volt will be the output voltage. Okay. So what is the output voltage? The options were plus 0.5, plus 2, plus 1 volt and minus 0.5. The correct answer or the output of this circuit is nothing but minus 0.5 voltage is the output. The phenomena of creeping occurs in dash. A ammeter, B voltmeter, C energy meter, D none of this. Correct answer is energy meters. And if the options, in the options there were wattmeter, the answer is wattmeter. Okay. So this creeping is a phenomena in which there is for finding the energy or for wattmeters there are coils, aluminum coils or aluminum disc. This disc rotates even when no load is connected. So we connect a load to measure the energy or power. Even when no load is connected, due to some errors, this coil or disc rotates and this rotation is called creeping. Okay, so this happens generally in the meters where we used to measure power or where we used to measure energy. Correct answer is energy meter or watt meter. If it is given in the option, the correct answer is that. Next question, a CMOS amplifier when compared to a N-channel MOSFET has an advantage of dash. It is having a higher cutoff frequency. Higher cutoff frequency is compared to that of a N-channel MOSFET. CMOS is having higher cutoff frequency as compared to N-channel MOSFET is the answer. Moving on to the next question. Early effect in bipolar junction transistors is due to dash. So, if you see a bipolar junction transistor, it will, I'm going to draw a rough figure. There is a emitter, there is a base, there is a collector. Okay, so there is a, if this is a NPN transistor, then this junction, emitter base junction is forward bias. Then it is like this only. And for the collector base junction, it is reverse bias. So it will be like this. So this collector base junction will get pinched off early or due to the, pinched off, the depletion layer will grow and it will get pinched off early, and this effect is called early. It happens in BJT and also in CMOS or MOSFETs. So in MOSFET we know that it is due to the drain voltage. Here it is due to the high reverse bias of the collector base or the base collector junction. This pinch off, this early effect is happening. So the early effect in the transistors is due to the high reverse bias of the collector base junction. Okay, the correct answer is nothing but this reverse bias of the collector base junction causes the early effect or the pinch off of this junction. Unit of mobility is dash. This is a direct theory question. The unit is meter square volt raised to minus 1 second raised to minus 1 is a unit of mobility. So we have used mobility in a lot of questions, but the unit is this, meter square volt raised to minus 1 second raised to minus 1. Next question, diffusion capacitance of a PN junction dash. The question is regarding to the curve of the diffusion capacitance, that is its a relation with that of the forward bias voltage. The options were it exponentially increases with forward bias voltage or it exponentially decreases or it linearly varies. The correct answer, if you see the curve of diffusion capacitance, it is like this. If this is the forward bias voltage and this is the diffusion capacitance, then the diffusion capacitance exponentially increases with that of the forward bias voltage. Okay, so due to the applied voltage, it exponentially increases. That is a case of the relation of diffusion capacitance and voltage applied. Okay, so the correct answer is it exponentially increases. Moving on to the next question. These are basic theory questions. Okay, junction capacitance of a PN junction depends on dash. A, doping concentration. B, applied voltage only. C, both doping and applied voltage. D, barrier potential only. The correct answer is it depends on both doping concentration and also applied voltage. Correct answer is option C is the correct answer. Next question is regarding the operating point or operation point of the transistor. The question is operating point of the transistor amplifier represent dash. I'll read out the options. values of IC and VC when signal is applied, 0 signal values of IC and VC, the magnitude of the signal, value of IB and IC for full signal. Okay, so if you see the cara of the IC and VC of this transistor, it will look like this. This will be the cara, right? And if you draw a point here, you can represent the saturation point of the transistor, and this is the cutoff point. And if you draw a line between these points, it is called the load line. You should know this term also. This is called load line. And the point on the load line which cuts or meets this cara of IC-VC cara or the transistor cara is called Q point or operation point. We call the Q point as operation or operating point of the transistor. So this is nothing but the cara or the curve between IC and VC. So these are the questions which I have included in this video. We will be doing the last part. Some of the circuit problem questions are a little bit confusing since the answer key is not out. So that is why I am making a little bit delay. There is only 2 questions from the circuits. One for a Wheaton's bridge and the next question is regarding the current flowing through a circuit. Only that 2 problems is left out and all the other important questions we have discussed. Okay, so this is the part 4, part 1, part 2 and part 3. I have already discussed a lot of questions in these videos. So I hope that these videos will be useful for your preparation for those people who are preparing for HSFC, SDSC, VSSC. Now you are Rao Center and a lot of recruitments is going to happen. And similarly, all the other the firms also. HAL is also calling for technical assistant. There is a lot of vacancies and job openings for diploma people now. So for you guys, these videos will be useful. I hope you are gaining a lot of knowledge from these videos. If yes, please do give it a thumbs up and also share these videos maximum with friends. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.